Hello everyone, welcome to Tau Beta Pi Drawing Board. Today we are going to learn about integrating factors. So integrating factors are functions which are used to solve differential equations. Also, integrating factors can be multiplied to ordinary differential equations to make the function integrable. Also, integrating factor is used with multivariate calculus. Also, it helps in transforming inaccurate differential equations into accurate differential equations. So, if we are given a differential equation of a form dy over dx plus a function p of x multiplied by y is equal to another function q of variable x, the integrating factor becomes mu is equal to exponential e raised to power integral of p of x dx. Now we will look into a general statement for the integrating factor equations. Let's consider an ordinary differential equation which we want to solve. So we can use integrating factor to solve that ordinary differential equation if the equation is of first order, meaning dy over dx is the highest derivative in the equation. Second condition being if the equation is linear, meaning that each term should involve a term related to y as either dy over dx or a single factor y. So the equation should be able to rearranged or reordered to look in a form like this. So if we are able to satisfy these two conditions and rewrite the equation such in this form, so we can use integrating factor to solve that ordinary differential equation. One thing to note, p of x and q of x are functions of x and they can also be constant. Okay, so now let's look at how we got the integrating factor equation and let's derive them. So let's say we have a ordinary differential equation of form dy over dx plus px y is equal to q of x. Okay, so let's multiply both sides by a positive function. Let's call it mu of x and it should be greater than 0 at all times. So after multiplying the equation, the positive equation on both sides, we get mu of x dy over dx plus mu of x px y mu of x q of x. Okay, let us say that d mu over dx is equal to mu of x and p of x. Now let's solve for mu. So separating variables on both sides, we get 1 over mu d mu integrating on the other side integral of p of x dx and plus a constant c. For now we can say constant is equal to 0 to make the calculation easier. Okay, so integrating we get natural log of mu integral of p of x dx. So once we get this equation, take exponents of both sides, we get mu is equal to exponent raised to power integral of p of x dx. So this becomes our integrating factor. Okay, so what can be a general solution using integrating factor? So let's try to input this equation. In the first equation, the ordinary equation, we had this one. So the general solution can be written as mu of x dy over dx plus d mu of x over dx y mu of x qx. Okay, now so on this side we can see it looks like we are taking a derivative of product of two functions, so we can go back a step and rewrite it as d of mu x y over dx is equal to mu x q of x. So taking integral on both sides, we get mu x y integral of mu x qx dx plus c, and refining this one step more, we get y is equal to 1 over mu x in bracket integral of mu x q of x dx plus c. So this is a general solution by using integrating factors. So now let's look at few of examples using integrating factors. For first example, we are given this ordinary differential equation, 1 over x dy over dx minus 2 over x square y is equal to x cosecant of x, and x is always positive. Okay, so let's rewrite the equation into a standard form. That becomes dy over dx plus p of x y is equal to q of x. So similarly following it, dy over dx negative 2 over x y is equal to x square cosine of x. So our p of x is negative 2 over x, q of x is x square cosine x. Okay, so let's first compute the integrating factor, okay, which is of form mu of x is equal to e raised to power integral of px dx. Okay, similarly writing it back, we get mu x is equal to e raised to power p of x, which is negative 2 over x dx. Okay, which results in e raised to power negative 2 natural log x, and taking 2 over x we get e natural log x square negative x square, sorry, x raised to power negative 2. So our mu of x becomes x raised to power negative 2. Now let's look at the general solution, which should be of form y is equal to mu of x in bracket integral of mu x q of x dx plus c. Okay, so inputting those values in this general form, we get y is equal to 1 over x raised to power negative 2 integral of x raised to power negative 2 x square cosine x dx plus c. Okay, solving it further, 1 over x square integral of, because this will cancel out each other, we are just left with cosine of x dx plus c. So in the end we get x square sine x plus c, for x being always positive. So this is our solution to the differential equation. Okay, so let's look at another example. So in this example we are given dv over dt 9.8 negative 1 over 5 v, and we are given a condition v at 0 time is equal to v naught. So this is an equation for velocity with changing over time. Okay, so let's rewrite into a standard form. We get dv over dt 1 over 5v is equal to 9.8. So p of x, in this case p of t is 1 over 5 and q of t is 9.8. So looking at the integrating factor, we get mu of t e raised to power 1 over 5 t dt, sorry, which after solving gets e raised to power 1 over 5 t. Okay, the general solution becomes v of t e raised to power negative 1 over 5 t in bracket integral of 9.8 e raised to power 1 over 5 t dt plus c. Solving it, we get e negative 1 over 5 dt in bracket 49 e 1 over 5 t plus c. Taking this exponential term inside, we get v of t is equal to 49 plus constant c with e raised to power negative 1 over 5 t. So because we are given a condition, or what you call a state, we can calculate the constant c using this. So the solution we got from the general equation was Vt is equal to 49 plus constant c with e raised to power negative 1 over 5 t. Okay, let's try to find the constant, the value of constant. So we know that v at time 0 is v naught, which means at t is equal to 0 v becomes v naught. So therefore, substituting this in the general solution, we get v naught is equal to 49 plus c e raised to power c e raised to power negative 1 over 5, and t is 0. So we get a c v naught minus 49. Okay, so our final solution with the constant term c becomes v function of t with 49 plus in bracket v naught minus 49 e raised to power negative 1 over 5 t. Yeah, so that's all for today. Thank you for watching Tabita Pi Drawing Board. See you next time.